Alright, this video is part of the Equilibrium 2 series. Here we're taking a look at the possible formation of precipitates. There's a lot of math in these videos and a lot of steps, so I highly suggest that as we go through a step, you take the time to maybe pause the video and write out what I've written, or let me go through with the lesson and then go back and go through it stage by stage again, just to sort of wrap your brain around what we're doing here. So in the first case, we're taking a look at the addition of two salts in a double displacement reaction. We need to determine if a precipitate will form. Now you need to remember that not all salts are the same in terms of solubility. And once you reach that point of saturation, depending on how well that salt will dissolve into water, precipitate may form. And sometimes when you add two different salt solutions together, you get a double displacement reaction in which the new combination of ions will form a salt that has a very low solubility. And that will then that salt will then precipitate out a solution. So in this case we have an example of silver nitrate being mixed with potassium chloride, and we're going to determine if there is any chance of one of those new salts precipitating out. So the two possibilities of salts are silver chloride and potassium nitrate. And we take a look, our KSP values for silver chloride, it's 1.8 times 10 to the minus 10, and potassium nitrate is 173. So right now we need to ask ourselves a question. If KSP is large, what does that mean? If KSP is small, what does that mean? Well, just like with an equilibrium reaction, remember it's products over reactants. In this case, KSP, we just look at the dissolved ions. So if my KSP is large, that means I produce a lot of dissolved ions. If my KSP is small, I do not produce a lot of dissolved ions, meaning the salt will not dissociate. So right here with potassium nitrate, we can see that we can put a lot of potassium nitrate into a water solution and have it dissociate. It will dissolve. However, silver chloride, 1.8 times 10 to the minus 10 is a very, very small number. Hence, it will most likely be this salt that has the potential to precipitate out. So the first step we do in a question like this is we need to determine the chemical reaction, in this case the double displacement, and which products may potentially precipitate. So we take a look, and I like to draw out my equation like this and put my KSP values underneath. And again, as we can see, this value is very small, so this is the potential value for the potential salt that may precipitate. So step 2, we need to determine the number of moles of each ion in the silver chloride that may precipitate out. Then determine the concentration if, say, these ions fully dissociated into solution, because that would be the concentrations that we use to determine if they've gone past that point of saturation for silver chloride. So first we'll take a look at one of the ions, and this is silver nitrate. So when we take a look at, and again we're going to find moles first of silver nitrate, and then using moles we can determine concentration. C for concentration, and for moles, of course. So we look at our silver nitrate because that will give us information about how much silver we have, silver ions. So moles is concentration times volume. We can see moles per liter times liter. The liters we cancel out and we'll be left with moles. Now what I did here was, if we look at the question, we were given our volumes in 25 milliliters. Right away, I didn't write it down, but right away whenever I'm given a question like this, bang, convert it to liters. If you don't you're going to be in a lot of trouble. Sometimes you're given solubility in terms of grams per 100 milliliters. Again, convert that to grams per liter and then go right to moles. In this case, we're given a volume of 25 milliliters. I converted that to liters right off the hop. So I multiply my molarity by my volume, and I get 2.5 times 10 to the minus 4 moles. If we take a look at the ratio between silver and nitrate ions in silver nitrate, it's 1 to 1. So one silver ion will be produced when one formula unit of silver nitrate dissociates. So 1 mole of silver ions for every mole of silver nitrate. And so hence you see most silver ions, that would be the same as your moles of silver nitrate. So then we can just easily go and solve for the concentration. Now, put a little star here, because remember, we're taking 25 milliliters of one solution, adding it to 25 mils of another, and what does that give you? A new solution that has a total volume of 50 milliliters, or in this case 0.05 liters. This is a part where people will make mistakes. You have to be careful about that. Alright, when you finally go to find the concentration of your ions, and this is an ion here, so I should probably include the charge, you want to make sure that you added those two volumes up. Now, we need to do the same thing for the potassium chloride and see what our chloride ion concentration is going to be. So again, first I solve for my number of moles of potassium chloride, and again I do a very similar math, putting the correct concentration in, and I get my number of moles of potassium chloride, which is the same number of moles of chloride ions. Again, this is an ion, so we need to include our charges. And from that we can very easily determine the concentration of chlorine ions in solution. And I get 5.0 times 10 to the minus 3 moles of silver ions and 2.5 times 10 to the minus 3 moles per liter of chlorine ions. So my next step, step 3, we need to write our equilibrium expression for the dissociation of the target product and compare the solubility quotient with the KSP value to determine if the saturation has been exceeded or not. So in a nutshell, what we're doing is we need to compare our KSP value to hypothetically how much what our solubility amount would be for putting these two ions together. So if we take a look, our KSP value is 1.8 times 10 to the minus 10, and we would get that by multiplying our concentration of silver ions and chlorine ions at saturation together to get that. And they would have to be in a certain ratio to give us this answer. Alright, that's at saturation. We need to see if we've gone beyond that. So our solubility quotient is pretty much the same thing. We take a look at our concentrations, and hypothetically, if we put these two solutions together, and we'll see if we've exceeded that. So we put in our concentration of silver and our concentration of chlorine ions. We multiply them together based on the equilibrium expression, and we get this number, 1.25 times 10 to the minus 5. Now what we do here is we do a comparison, and it turns out that Q is much larger than our KSP, so therefore the silver chloride will precipitate out. So this is an example of a question where you can determine if a reaction happens, if precipitate will form. We could take this a step further and actually determine how much precipitate would form, but we'll leave that for another lesson. Now we're going to move on to another problem, and that is, say we go to put a salt solution, and this is quite similar to the last one, or put some salt into a solution that already contains another salt. This case, the two salts have a common ion. So in this question, we're determining what is the solubility of lead 2 chloride in a 0.2 mole per liter sodium chloride solution at SATP, standard atmospheric temperature and pressure. Now, our common ion is a chlorine. So we have a chlorine ion in the lead 2 chloride, and we'll have a chlorine ion in the sodium chloride. Now, we've already got a solution of sodium chloride. So our first step, step 1, is to determine the initial concentration of chlorine ions in solution due to the presence of the sodium chloride. So how much chlorine do we already have in solution? So that's a pretty straightforward calculation. We look at how sodium chloride would dissociate, how it would break down, check out the molar ratios, 1 to 1. So if I know my concentration of the salt, it would be the same as my concentration of either ion, which is 0.20 moles per liter. Our next step now is to find the KSP of lead 2 chloride. We go to that in a table. In our textbook, it's table C8. And you could easily find it on the web. And we need to establish our ice table with the initial concentration of the chlorine ions that we got from the sodium chloride solution. Then we're going to determine, using the ice table, what our KSP expression will look like using any variables that we've created. So let's take a look at what this is going to look like here. Well, from doing a little bit of research, we find our KSP is 1.2 times 10 to the minus 5 for lead 2 chloride. And this is potentially what could precipitate out. We're adding lead chloride in, but there might be already too much chlorine in the solution, and it could precipitate out the lead 2 chloride. Remember, sodium chloride has a very high KSP, 38.65, something like that, and you could put over 300 grams of it in a liter. But obviously the lead 2 chloride has a much smaller KSP. So now we determine our ice table, and this is how we set up our ice table right here. I like to set mine up just like a chemical equation, and I put my brackets around my ions and any coefficients outside the brackets. So of course, because our lead 2 chloride is a solid, we cannot change its concentration. It remains constant. And this is where things are different than they usually are for equilibrium type questions that we've done. We're not going to start off with any lead in the solution. However, we're adding a salt to a solution that already has chlorine ions. And those chlorine ions already have a concentration of 0.2 moles per liter. That's why I put a little star beside there, because there is an initial concentration of chlorine ions. Now, of course, we're going to add X amount of lead, and we're going to add 2X amount of chlorine because of that 2 in front. That's our coefficient. So when lead 2 chloride dissociates, for every ion of lead that I get 2 ions of chlorine. Hence, my equilibrium concentration for lead would be X, but for chlorine would be our initial concentration plus whatever we're going to add. And sorry, that should be a 2X right here. Quickly fix that up. So we'll have a 2X, 0.2 plus 2X. So what will our KSP expression look like? Well, we have our lead ions and our chlorine ions, but again, because we have that 2 as our coefficient, it now becomes an exponent. So we sub in what we have in our equilibrium section of the ice table, X and 0.2 plus X. Now, just like we did when we did equilibrium calculations before, we're getting a potentially complicated question here. What we have to do is compare our initial concentration to KSP. Remember the old IC over K? And if it's greater than 1,000, then we don't have to worry about what change is happening at equilibrium because it'll be so small we don't have to worry about it. Well, in this case, that's what we're seeing here. because it's times 10 to the minus 5, our KSP value is so small compared to our initial concentration, we actually don't have to worry about X. So we can cross that out, and we get our KSP expression, and our KSP value is 1.2 times 10 to the minus 5 is equal to X, because our lead we will have to worry about, times 0.2 squared. We don't have to really worry about the extra, the addition of the 2x. That should be a 2x there. We don't have to worry about that because that is going to be so small. So very similar to the calculations we did before. So now, what's this going to look like? So we substitute everything in. So now this just becomes a plug and play. I just took what we've seen here and I plunked it there, rearranged it, kind of flipped things around so that I got my x on the left and my numbers on the right, and I solved for my x value, which is 3.0 times 10 to the minus 4. So what does this mean? That means that the molar solubility of the lead to chloride in a 0.2 molar solution of sodium chloride is 3.0 times 10 to the minus 4. So it's sort of like a KSP value, but instead of it being for water, it's a KSP value, you could think of it, for a solution of salt, table salt, sodium chloride that has a specific concentration already. And what I did here at the bottom was we checked our assumption that we did before, that this change in our initial concentration wasn't going to be too much. So we're going to check it now that we've solved for x here and it's really small. Let's see what the effect of 2x, adding the 2x on the 0.2 initial concentration would do for the concentration of chlorine. So 2x would be 2 times 3.0 times 10 to the minus 4. We get 6.0 times 10 to the minus 4. Now if we add that to our initial concentration, we'll get a number that looks like this. We'll get 0.2006, which is really small. Because this is 3 decimal places away from the 2, we don't have to worry about that at all. So it's just 0.2 moles per liter. So we can see this change right here is so insignificant to the initial concentration, we don't have to worry about it. And so to go back, whenever you do a question like this where you now have the potential for some messy quadratic equations to pop up, always check your IC over K ratio. And if it's greater than 1,000 or even greater than 500, we can just assume that X is not a factor in that one section there. Of course, we need to worry about for the other ion.